In this video, we're going to take a look at the basic properties of field effect transistors and how such transistors in the form of CMOS can be used to implement digital logic. Let's look at some terminology first. FET stands for field effect transistors. And then a MOSFET is a metal oxide semiconductor field effect transistor. And then there are two different types of MOSFETs. There are N-channel MOSFETs and P-channel MOSFETs, and they are referred to as NMOS and PMOS transistors. And finally, the CMOS transistors, from which most modern digital logic circuits are made. CMOS stands for complementary metal oxide semiconductor, and CMOS transistors is essentially a combination of using both NMOS and PMOS transistors. The schematic symbol of an NMOS transistor is shown here on the left. There are four terminals. There is the gate, there is the source, the drain, and the body of that transistor that are shown in this picture here. If we look at the actual implementation of such a transistor, then we have here at the bottom the body, and that is made for an NMOS transistor from a P substrate. Now P and N refer to silicon or some other semiconductor material that has been doped either with electrons, so there are additional electrons in there, and then we call it an N-doped semiconductor material. And if some electrons are missing or holes have been inserted, then we talk about the P-doped semiconductor material. So the body of an NMOS transistor is made from a piece of silicon or other semiconductor material that has some electrons missing, and we indicate this here by showing plus signs in that P substrate. Inside that P substrate, then two channels are put in with N material. The N plus stands for highly doped N material. So that's N material, N-doped material, which has lots of electrons, lots of extra electrons in it. So this is highly N-doped. Okay, so there are those two channels here with the N-doped material. Those form the source and the drain. And then there is a piece of insulation put here. So this gray piece here, that's insulation. And that's where the oxide in the metal oxide in the MOSFET transistor comes from. Okay, oops. Okay, the metal oxide semiconductor field effect transistor. So the O, the oxide, is actually this insulating material here. It's often made from silicon oxide, but it can be other forms of oxide or insulation as well. And then on top of it is the gate. So this part here, this is the gate. Originally that was metal that was put on that oxide, or in fact it even consisted just of aluminum that then was oxidated on the lower side so that it formed an insulator. And in modern transistors, this is often made from polycrystalline silicon. Okay, so this is the gate. And so this corresponds to the four terminals that are shown over here. Okay, in practice, we often use a simplified symbol, which only shows the source, the drain, and the gate, and it doesn't show the body. Typically, the body of an NMOS transistor is connected together with the source. Now, the transistor gets interesting when we can use it either for amplification or for switching things on and off. For digital logic, we use it as a switch to switch things on and off. So going back once more to this original structure here, we don't apply any voltages here, and those two highly n-doped areas here are insulated from each other through the P substrate that's in between them. So there's no current flowing between the source and the drain if we do not apply a gate voltage to this structure. And that would correspond to an open switch between the source and the drain. Okay, so that is actually shown down here. If the gate voltage is low, or we just simply don't apply any gate voltage, then we have an open switch between source and drain. Now, to turn the transistor on, we use a voltage source to place a positive voltage on the gate. Okay, so that that acts a little bit like a capacitor, and so there are positive charges here on the gate, but they cannot get past the insulation that's in between here. So here we have insulation, and the electrons cannot get through that insulation. However, they create an electric field, and on the other side we're getting all negative electrons. Those are essentially being pulled out of the P substrate. There's of course still electrons in there, so whatever electrons are available are actually coming to this junction here because of the electric field and the positive charge on the other side. Now that creates a channel here so that we actually start getting conduction between those two n-doped channels here. Okay, so this here is referred to as a channel. And once the channel is established and current can flow, then we have current flowing in the conventional positive flowing sense from the drain to the source. In the sense of actual electron flow, it flows from the source to the drain, and that's actually where the name source and drain are coming from. Here's the source of the electrons, and then it flows over to the other side, to the drain. So when the voltages are applied like this, then we have a switch that is closed, and in this case the gate voltage is high compared to the base, to the body, and compared to the source as well. Notice that here body and source are both connected to ground, so they are essentially connected together. Now if we change everything that's positive to negative and everything that's negative to positive, then we get the opposite type of transistor, and that's the PMOS transistor. The schematic symbol has again 4 terminals. There is the body. The symbol is shown upside down here with respect to the NMOS transistor, because the body for a PMOS transistor is actually connected to the positive voltage. So that is shown here. And we have the drain and the source as well, and the gate. The little circle here on the gate indicates that this is a PMOS transistor, and that this switches in the opposite way as a NMOS transistor does in terms of the voltages that are being applied. So the physical structure is such that the transistor is started from an N substrate, so that's a piece of silicon or other semiconductor material that has excess number of electrons in it, and then 2 regions with P plus, again this is highly doped P material, are inserted, but the 2 regions are insulated from each other because of the N substrate, unless some external voltages are being applied. Okay, here's again the insulation between the gate and the N substrate, or the body of the transistor, and then the gate itself is this part here. Again, this is shown upside down because PMOS transistors are usually used to pull things up to the positive power supply, whereas NMOS transistors are used to pull things down to the ground. Okay, and the drain and the source, those are the connections to those two positive doped regions inside the body of the transistor. So this is a switch which is in the off state when no voltages are being applied. Okay, so that is shown here. When Vg is high, then nothing is flowing, the switch is open. But if we put the gate to ground, like it is shown here, the gate is now connected to ground, then we will see that we get the closed switch. And the way this happens is very much the same as for the NMOS transistor, except for the polarities being reversed. So now, because this is put to ground, we have negative charge on the gate, and that negative charge cannot go past the insulation. But on the other side, all the positive charges are concentrating, and they form an electric field here, similar again to a capacitor, and that creates a channel here between the two P regions where current can flow. Okay, and so now if the source is connected to the positive supply voltage, same as the base, so again at the body, again the body and the source are connected together essentially, then the drain voltage becomes equal to the high voltage, the VDD voltage, the supply voltage. And so it acts like a closed switch that pulls the drain voltage up to VDD. Here's the simplified symbol of a PMOS transistor. It looks exactly the same like it does for the NMOS transistor, with the exception here of that little circle, which is our indication that it is PMOS instead of NMOS. Notice also from the drawings here, you can see that the drain and the source region are pretty much interchangeable. Okay, so it doesn't really matter which one we think is the which one is the drain and which one is the source contact here. It is entirely symmetric and similar for the NMOS transistor. So we often do not actually show on the simplified symbol what the drain and the source is, because we could have used either of them. The simplest circuit that we can build, simplest logic circuit that we can build from transistors is a NOT gate. Okay, let's first look at the case where we are using switches. So the dashed gray lines here indicate that those two switches are mechanically connected together. If the upper switch is open, then the lower must be closed, and vice versa. If the lower is open, then the upper must be closed. Okay, that's just mechanically connected that way. So we are thinking of X, the input of the inverter, being equal to 1 if the lower transistor is closed and the upper transistor is open. Okay, for an inverter, if X is equal to 1, then the output has to be equal to 0. So in order to make the output equal to 0, we close the lower switch and leave the upper switch open. We cannot have both switches connected at the same time, otherwise we get the short circuit between the supply voltage and the ground. And then if we want to change the input to 0, we change the switches. So now the upper one is closed, the lower one is open, and that pulls the output to high. And so what we get in this case is, if we have a 0 here, then we get the 1 here. And here, when we had a 1, we get the 0 at the output because it's being pulled down to ground. Now we have just seen that PMOS and NMOS transistors can act as switches. And we have also seen that the NMOS transistor, the body is connected to ground. For the PMOS transistor, the body is connected to the supply voltage. So that then leads us to this circuit over here. So now we have two transistors, one PMOS and one NMOS transistor. The NMOS transistor acts as a switch that can pull things down to ground. The PMOS acts as a switch that can pull things up to the supply voltage. And because they are complementary with respect to each other, therefore the name CMOS, at any time one of the switches is open and the other one is closed. So if we put a 0 here at the input, then the gate of the PMOS transistor is pulled down to ground, and so the PMOS transistor is on. So that's shown here. And at the same time, when we put the 0 to the gate of the NMOS transistor, then the NMOS transistor is turned off, and no channel is being formed here. And so that is the off state here for transistor 2. If we, on the other hand, put a 1 at the input, then the NMOS transistor has now a positive gate voltage, and the channel is being formed here, so it acts like a closed switch. So this is on when we have a 1 at the input. And if we have a 1, then the gate of the PMOS transistor is connected to the supply voltage, so it's equal to that VDD here, and that turns the transistor off, and we have T1 in the off mode when the input X is equal to 1. So we can go back and forth between 0 and 1, and that will create the corresponding output here. So when we have a 1 here, Vf will be 0. And when we have a 0 at the input, Vf will be VDD corresponding to logical 1. Now here's the schematic of such an inverter in a SPICE simulation. This was done in LT SPICE. And up here we have the PMOS transistor, and down here we have the NMOS transistor. And we use the transistor symbol here where the body is actually connected directly to the source in both cases. So this middle terminal here is the body. In this particular case, the schematic symbol is made in such a way that the distinction between PMOS and NMOS is given by the arrow here on the body terminal rather than on the circle at the gate. So in terms of what we have just done before, we would actually have that little circle here on the gate to indicate the PMOS transistor. So the 5 volts over here, this is the supply voltage. And over here is the source voltage, so that is Vx, the input of the NOT gate. And over here, the Vf, that's the output from the NOT gate. Transistors are called M1 and M2, and we're also going to take a look at actually the current that flows here through the M1 transistor. So this is the ID, actually IS, the source current of M1. Okay, and we're going to simulate this for 1 microsecond, and the voltage source here is set to actually make a pulse with some rise time of 0.1 microsecond, fall time of 0.1 microsecond, and it goes from 0 to 5 volts and then back to 0 again. So here's the result of that simulation. The green curve here comes from the input to the gate. So we have an input of 0 here. So this is Vx. And here we have Vx corresponding to 1, so that's VDD. And then it goes back down again. and back to 0 again. And then the output is in blue here, so this is the output that we get from that circuit. You can see that even though the input was made deliberately somewhat slow, the output actually goes down very rapidly. So we have a rapid transition from the VDD down to ground or 0 volts and then back up to VDD again. So here we have VF is equal to VDD corresponding to a logical 1. Here VF is equal to 0 volts corresponding to a logical 0 and then back up to 1 again. So it does indeed operate as an inverter or as a NOT gate, and it goes nicely between 0 volts and 5 volts. Now the interesting thing is to look at this red curve here. That is actually the current that flows into the source of the upper transistor of the PMOS transistor. Because both transistors are in series, it's actually the same current that also flows through the NMOS transistor at the bottom. And we can see that the 0 of the current is this line here. So we have actually 0 current most of the time, which is a nice advantage of the CMOS structure of implementation. But we do have spikes here that go up to fairly high levels in this simulation. Here we have 180 milliamps. Those spikes are of very short duration in a real circuit. They are somewhat longer here because of the time scale was chosen to be relatively drawn out. But those spikes here, those current spikes, they are a real feature of actual CMOS logic. And those are actually the reasons why bypass capacitors are necessary close to the integrated circuit, because during that time, there's a short time when both of the transistors are actually conducting, and that is driving that high current. And the energy for doing this needs to be delivered from somewhere. And the best way to deliver it is from short-term storage, which is given in a practical circuit in the form of those bypass capacitors. Okay, so that's the reason for the 0.1 microfarad capacitors that you should put nicely distributed over all the different integrated circuit packages. When people talk about integrated circuits, and in particular CMOS integrated circuits, there is often talk about the geometry of such circuits and about the smallest feature, for example, that can be implemented for a given technology. And what people refer to when they talk about that is to the channel lengths and the channel width, which are shown here in this drawing of an NMOS field effect transistor. So we have again the P substrate, and we have the two n-doped channels or regions here on each side, and in between we have just the P substrate, which insulates those two n regions from each other if no voltage is applied to the gate. And if a positive voltage is applied, we generate the electric field between the gate and the P substrate, and that attracts electrons or negatively charged particles down in here, and we create a channel between the two. So this place here is where the channel forms, and the transistor is on when the gate voltage is set to VDD. In order to place as many transistors as possible on an integrated circuit, people try to make the dimensions of those transistors as small as possible. There are some limitations, technology limitations mostly, as to how narrow this can be made. And currently, 35 micrometers is what people do on regular integrated circuits. some special cases they go lower than that. That's a very small number. It's actually, just realized it should be 0.35 micrometers. Okay, not 35 micrometers. This is a very small length here, or distance. Compare this to human hair. Which is approximately 100 micrometers in diameter. Okay, it varies a little bit. Some people have thinner hair and some have thicker hair, but 100 micrometers is a good rule of thumb. So you can see that this is about 300 times smaller than a human hair. That's the distance here between those two. That is what's forming the channel. And then there is also the channel width. That's the other direction here. When you look at the gate, the area of the gate is L times W. Okay, so this has area L times W. So now, when you build circuits like that, one important consideration is how fast can those circuits work. And this is primarily determined by the propagation delay as signals go through that channel here, and how well they can then drive the output as the current goes through that channel and then to the output of the transistor. So here is a typical setup for this. So this is an OT gate, and we have again the PMOS transistor and the NMOS transistor, but I have now included here a capacitive load, which comes from various things. It can be parasitic capacitance from wires that are close together. The gate itself also forms capacitance between the P substrate and the gate, or the body and the gate of the transistor. And when the switches here switch from one state to the other, then that capacitor needs to be either charged or discharged rapidly. Okay, so that essentially determines how fast that logic can operate. And it turns out that the propagation delay is approximately given by this formula here. Okay, K here is some constant. And then the propagation delay increases with increasing load capacitance. That makes sense. It decreases when the voltage, the supply voltage, is larger, because that charges the capacitor more rapidly. And then going back to the geometry here of the transistor, we have L, the length of the channel. If that length becomes larger, then the propagation delay becomes larger, because the resistance of the channel here becomes larger. And if the width becomes larger, then the propagation delay actually decreases, because then we have more area underneath here. The whole channel area is going to become larger, and that decreases the resistance, the overall resistance of the channel. So the geometry of a NMOS or PMOS transistor is an important consideration when people are designing and implementing integrated circuits for digital logic.